This video was developed to help explain a few basic principles in the identification of process safety risks. It describes a model that explains several key principles for assessing and managing the risks from losing containment of a hazardous substance. This model is a hybrid of various industry models. A qualitative process hazard analysis is a common approach used to identify the risks of a process and to evaluate if there are sufficient safeguards in place to manage these risks. Many businesses are taking a more quantitative risk-based approach to process safety in order to consistently realize a vision of zero process safety incidents, which are those that result in an injury, environmental impact, property damage, or business interruption. We'll use a fictitious scenario from a storage tank of flammable liquid to describe this model. This example is not intended to illustrate an acceptable design approach, but to illustrate some basic concepts concerning process safety risk management. In this example, we'll be refilling a tank of flammable liquid and assume that the process is designed so refilling the tank is safe under normal operating conditions. In this example, we'll use a level transmitter malfunction as the deviation or initiating event. The malfunction causes the transmitter in the tank to incorrectly read a low level. As a result of the malfunctioning level transmitter, the process control system believes the level in the tank is too low and a truck is automatically ordered. We now need to determine if there's a consequence of interest. If the truck is allowed to unload when there is insufficient space, the tank will overflow, creating a pool of flammable liquid in the secondary containment area, forming a flammable vapor cloud. The vapor cloud could ignite, resulting in a flash fire and fatality of the person unloading. Indeed, this example does have a consequence of interest. The malfunctioning level transmitter leading to a flash fire with fatality is called a cause-consequence pair, or a scenario. This model illustrates the progression of the initiating event to the final consequence with a laser that starts at the deviation and continues to the right until it reaches the final consequence. Risk can be defined as a function of the likelihood that an initiating event could lead to a specific consequence. In our example, the scenario being evaluated is the likelihood that the malfunction of the level transmitter starts a chain of events. These chain of events lead to a release of flammable liquid causing a fatality from a flash fire. The risk can be reduced by reducing the severity of consequence or the likelihood. Our model will illustrate the reduction of risk through the implementation of safeguards, often called layers of protection. These layers of protection can be procedures, personal protective equipment, management system processes, or devices that are designed specifically to prevent the escalation of the deviation to an undesired consequence. In the model, layers of protection that reduce the likelihood of the event are illustrated as disks. These are inserted between the deviation and the final consequence. These layers block the laser beam, the deviation, from progressing to the final consequence. Layers of protection are not 100% reliable, but have a probability of not working when needed. This is called the probability of failure on demand. The holes in the disk represent failures of the layer allowing the laser to pass through to the consequence. As the reliability of the protection layer decreases, the number or size of the holes increases. The failure of the layer of protection is not predictable, but random. The model illustrates the randomness of the failure by spinning the disk. The initiating event is also random. In this example, we do not know when the level transmitter will malfunction, therefore the laser is randomly emitted. We'll now begin to identify the layers of protection for this scenario. The first layer of protection is an operator who uses a checklist from an approved operating procedure. This checklist is established specifically to determine if there is sufficient level in the tank to contain the entire contents of the truck before unloading. The second layer of protection is a high-level switch that shuts an unloading isolation valve when the tank reaches 90% full. If the first and second layer of protection fails to stop the progression of the deviation, then the tank will overflow into the surrounding diked area. We call this loss of primary containment. Once we lose primary containment, there are many factors that can affect how the scenario progresses. The tank might overflow 1 liter or 5,000 liters depending on when the level transmitter malfunctions. Will it be a hot summer day with a mild breeze from the south, or a cold winter night with a strong wind out of the north? These conditions affect what happens next. We use a prism to represent loss of primary containment. As the laser passes through the prism, the progression path is randomly altered, changing the location where the laser exits. All of the protection layers described up to this point are called preventative barriers, because if any of these layers work, they have prevented the tank from overflowing or losing primary containment. The layers of protection we place between the loss of primary containment and the final consequence are called mitigating barriers. Mitigating barriers are designed to reduce the severity of the consequence of a release. Although these barriers stop the progression towards the fatality, these barriers still have a consequence, although less severe. In this model, we use slices of Swiss cheese to represent mitigating barriers. Mitigating barriers also have a probability of failure on demand, and similar to the spinning disk, the failures are represented as holes. Secondary containment along with ignition source control is our first mitigating layer of protection. As described earlier, mitigating layers have consequences even when effective. In this example, the mitigating layers of protection consequences are financial costs for cleanup, loss of material, downtime, business interruption, and resources to manage the incident. These are all examples of additional consequences, but less severe than the fatality. The final mitigating layer of protection in this example is an organic vapor detector. The detector activates sprinklers for a fine droplet vapor suppression system, triggers a site emergency response system, shuts down all non-emergency equipment in the area, and sends out an automatic notification to the predefined emergency responders. If this initiating event in our example breaks through all 4 of these layers of protection, then the deviation could have the most severe consequence, a fatality. Now that the scenario along with the layers of protection has been defined, the analysis can begin to determine if the risk is managed to an acceptable level. We will not review the details of the analysis in this video, but in general, a team would evaluate the scenario and determine if there are enough layers of protection to reduce the risk to an acceptable level. This analysis can be qualitative and quantitative. We'll now transition from describing the methodology of evaluating risk to the most critical aspect of managing risk, leadership. The box surrounding this scenario represents the management environment of the process. The leadership we demonstrate within our area of influence affects the environment where we work. The quality of the environment is directly related to your level of operational discipline. Operational discipline can simply be described as doing what you say you will do. Low operational discipline within an organization creates an environment that is detrimental to the overall safe operation of hazardous processes. Over time, low operational discipline degrades the management systems that maintain the safeguards, and the safety systems become less and less reliable. Ultimately, layers of protection, both preventative and mitigative, can become completely ineffective and the risk increases. High operational discipline can be established and maintained with strong leadership commitment, collective knowledge of the process and its hazards, knowledge of the management systems required to help manage risks, and knowledge that operational discipline is critical to sustain an effective process safety risk management program. Once the organizational commitment and knowledge are in place, collective energy and effort are required to maintain the level of operational discipline necessary to manage operational risks. This effort comes from your core values and focus on safety. Individual and collective values of safety enable organizations to successfully manage the many risks present in their facilities. By managing risks appropriately, organizations are able to protect their people, communities, and the environment.